Hello, everyone. Today we are talking about a systems approach to design. And that sounds very exciting. So let's get into it. So, systems, depending on what you're interested in, um, what we call a flow chart actually is actually a pretty helpful way of visualizing how a procedure is going to work. Now, let's break this down into like a very relatable context. So here we have a street lamp or a set of street lamps. Now, the ones in Hong Kong, they automatically turn on at a certain point and they automatically turn off at a certain point as well. So it's reasonable to assume that given that daylight hours change over the course of the year, that the street lamps are actually controlled not by a timing circuit, but actually by a light level sensor that is on the top of each street lamp. Certain other countries around the world have drastically different hours of daylight throughout the year. I mean, the UK is a fairly moderate example, to be honest. But in winter, like bad day in the winter in the UK, like in January, it can be getting pretty dark. The light starts getting dark. If it's really cloudy, like even between 3:30 and 4, it'll start in the afternoon. It'll start getting dark, and then it doesn't get light in the morning until maybe 8. Whereas then in the summer, it can be light by 5 in the morning, and then the sun doesn't really properly set until maybe 9 p.m. or like between 9 p.m. and 10. So which is really nice, by the way. Long summer evenings are great like that. So the question is this: how do the street lamps know when to turn on and off? Sure, they've got a little sensor on the top, but we actually need to dissect a little bit more about how this actually works and what's the decision-making process. So it works like this: we have an input, a process, and an output. This is literally the fundamentals of systems design. So in the context of the street lamp, the input is the thing that is constantly sensing an external stimulus. So in this context, it's the light sensor on top of the street lamp. It's constantly checking the light levels, literally non-stop. It'll be checking it like multiple times every second. And programmed into the street lamp is going to be a certain level at which it'll deem it's too dark and it needs to turn on. And to do that, it has what's called a processor inside, and that's essentially the brains or the neural network of the products. So this is what actually does the decision making. It's reading the data it receives from the input. The input is just a passive. It's just a passive component. It doesn't actually think about anything. It's just constantly sending signals to the processor the whole time. And then the processor looks at the data and it's constantly evaluating how does that data relate to the benchmark at which it must then command the output to turn on. Let's say that the light level benchmark is 30 out of 100. 100 is full daylight and then 0 is complete darkness. So let's say 30 is like the value at which it must then turn on the output. So it's constantly checking the data it receives from the input. And the input will be sending like data the whole time, and it's reading. It'll be gradually going down during the day, and then when it gets to like say 31, and then 30, and then when it hits 29, it'll then think, oh right, okay, it's gone below that benchmark. I now need to tell the output to turn on. Or it doesn't even tell the output to turn on, it turns on the output. So the processor does all of the thinking and all the commanding, essentially. And then the output and the input are basically, they're just sort of, they're fairly basic components that just do as they're told. They're like the minions that do as they're told by the processor. You imagine the processor of the brain. In a human context, an input would be the equivalent of, say, our eyes. And our brain is the processor. If we walk into a room and it's a bit too dark to do whatever it is you need to do in there, maybe you need to do some studying or something, your brain will, not without even you thinking about it, it'll just think, oh, it's a bit dark in here, turn the light on. And in literally a split second there, your brain has done this cycle of input, process, output. It's your brain has processed that external information that your eyes, the input, have received, and then it processes that and it makes a decision. And it's like, okay, well, we need to turn the lights on. So the output there is the actual motor movement of your hand going for the light switch, because it's your brain telling your hand what to do. So yeah, that's essentially how systems work. Now, if we put this in the context of a flowchart, this is the basics of like programming. If you've ever used Microbit, Microbit uses a very simple, or can use very simple programming language, just called MakeCode or Block. It's just like block editing, and it's very similar to this. So in a flowchart, you'll have a start, which looks a bit like a sort of sausage, and then the decision making is a diamond-shaped box like this. So you turn on the circuit, and that's the start. So yeah, let's say this is this is just for like a simple I don't know, light in a room, which is just going to pulse on, then off. So the brain of the circuit is constantly checking: has the start switch been pressed? Has it been turned on? Has it been turned on? Has it been turned on? No. It keeps looping around there until it is switched on, and then it goes down to yes. Then the command is turn on the lamp. Then wait 2 seconds is the command, then turn off the lamp, and then that's the end of the whole procedure. Essentially, that's how programming works. It's constantly a chain of decision making and commands that are made. It's the same if you do a quality control flowchart in manufacturing. You sort of start a process, like it might be if you're, say, belt sanding a piece of timber down to just the right size, you'd start by turning on the belt sander. And maybe the first decision is the belt sander on? If yes, proceed to the next step. If no, try it again. First command might be begin sanding procedure. The diamond would be something like, have you sanded down to the mark? Yes or no. No, carry on. Yes, go to the next step. So basically, these little diamonds are points at which the circuit cannot progress until the step before has been done to a sufficient level, and then you can proceed to the next step. Okay, so looking at types of inputs, you guys need to know, this is very, very fundamental electronics. I used to actually teach, before AQA combined all the GCSE DT areas into one qualification. I used to teach DT electronics. And so that was when it was a separate qualification. So we had to know this stuff to a lot more depth. But now it's not nowhere near as bad. So inputs are things that can sense external stimulus. So think of your body for now. Let's think about the things that you can sense yourself. You've got your eyes, obviously. You've got your ears. It's like seeing head, shoulders, knees, and toes, isn't it? Eyes, ears, mouth, nose. Eyes, ears, mouth, nose, and then touch as well. That's the 5 senses we have, right? Now, we can actually replicate these things artificially. Smell is a tricky one. I mean, I guess there's probably is a sensor that can smell odor or can sense gas. Well, there is ones that can sense gas, that's true, or carbon dioxide. So yeah, there is an artificial version of that. So an LDR, this stands for light dependent resistor. Now, this is what would be used on top of a street lamp. Now, what these do is the resistance, so basically how much they stop the flow of electricity, is dependent on the light level. So these can be configured either way. So they can be set up so that when it's fully daylight and it's really bright, they will stop the flow of electricity. So they have full resistance. Or it can be flipped the other way. So when there's full daylight, it can be like, sure, go on through electricity. You guys, have your fill. Carry on down the circuit. That's basically what they do. They're like a gate where they can gradually let the electricity on or turn it off again. And it can be the same for dark. So if when it gets dark, it might be in the context of the street light. When it's light, it's like, electricity, you guys stay over there. I don't want you going anywhere near the brains of the circuit. Then as the light dims down, it's like, okay, all right, I can see where this is going. Okay, it reaches a certain level, and it's like, okay, right, I'm going to let you through now. That's kind of basically how variable resistance works. A thermistor is exactly the same, but for heat and temperature, hence the name thermistor, resistor and thermal put together. So it'd be more like sensing is something hot or cold, and that will then change how much voltage it lets through dependent on the temperature. Then another one is super simple. It's just what's called a push to make switch. This is literally like a switch on a mouse. It's just like a click, and it does something. All these do, they're like a little pulse of energy because you press it once and then let go, and it only pulses for as long as you press the button. So things like computer mice, when you click it, it sends it's like literally a fraction of a second, sends a tiny voltage to the brains of the circuits saying, oh, we got a pulse there. And then the brains will then process that information into doing something. This is the thing with electronics, everything happens instantly. Like there's literally no delay in things happening. So, and especially with processors now being as powerful as they are, they can process information literally instantly and multiple commands at the same time. Now, looking at processors come in a few forms. You get what's called a microprocessor. So it's like a microchip like this. Now, microchips come in different forms. You can have microchips which are pre-programmed just to do like one command or a couple of commands, and that's it. Or you get ones that are multifunctional, or you get ones that are programmable. Like you can actually tell them what to do. So all these different pins on here can be programmed to do different operations. You can say, right, actually, I'm going to link pin 2. It's going to be linked up to an LDR, and then pin, pin 5 or pin 6 around here is then going to go out to the light bulb. And then you program the microchip and you say, right, so when the LDR reaches this certain level and you start getting a bit of voltage here, we then want you to then turn on a switch inside, turn on the switch inside you to turn on the light. And so they're basically decision makers. That's really what they are. Now, a microcontroller, like this little microbit here, these are more advanced because these can perform multiple operations. Essentially, this is a very, very mini, very low-powered computer. It can compute lots of different things at the same time. So with these, they've got different sensors on them. So they've got like gravity sensor. They've got an accelerometer, so it can sense like gravity. It's got a thermistor on it. It's got an LDR on it as well. It's also got Bluetooth, which you can use other sensors from your phone as an input. It's got these pins at the bottom where you can link manual switches onto them as well. It's got a compass, so it can sense direction. It's got a ton of sensors on there, and that's why these are pretty fun because you can program them to do all sorts of very creative functions. And with that, you can then connect all sorts of outputs to them as well. So that's why now in computers they talk about like computers having X amount of processing power or X amount of RAM, or like Apple they're talking about the M1 chip that they've developed now, which is like their sort of Apple Silicon they call it, which is like super high powered. Tesla talk about their neural network that they've developed, which in line with the fully self-driving system they're developing for Tesla cars. Now that essentially is just one massive sort of synthetic brain that will make decisions based on this stimulus that the cars see. In Teslas, it's actually pretty simple. It's not simple, but in terms of the inputs and outputs, is that the inputs are literally just loads of cameras all around the car, constantly scanning for things that it's been programmed to recognize, like say red traffic light, like bicycle, car, person, whatever. And it's constantly feeding all that information to the car's processor in the middle. And then that processor is talking to the neural network that's like a sort of cloud-based system. And then that is constantly learning new things, and it will update what it does based on what it learns or what it sees. And then the output is either go, motors on, or brakes on to stop, or turn the wheels. And that's basically it. Sounds simple, but it's horrifically complex. So then outputs. So what sort of things can we then get a circuit to do? What can we get it to actually perform? Very simply, we've got light, movement, and sound. LEDs, bulbs, whatever, like a whole cluster of LEDs, super bright LEDs, whatever they are, they perform the function of giving out light. And motors, there's different types of motors, but essentially you get motors, which are like these, they just provide continuous movement, or you get what's called stepper motors or servos, which perform sort of very specific angles. So you can get a servo to change its angle by like 0.5 of a degree. It'll move by a tiny amount when it receives, based on what the processor tells it to do. An example of this is on an aeroplane. It's obviously got flaps on the back of the wing, which move depending on how much the pilot pulls the stick in the plane by, and depending on what they want to do, they want the plane to lift or go down or slow down or whatever. So those are servos that control that, because it might be that the pilot just wants to make a very, very minute adjustment to the flaps on the wing, just to change like whether they're going to go up or go down or whatever. And so the servos can provide tiny, tiny movement changes in that. And then obviously motors, continuous movement motors like wheels for cars, vehicles, whatever. Then speakers is obviously sound. And you also get what we call buzzers as well, that are more like, they use what's called piezoelectric material, which they vibrate to create like a horrible buzzing sound. Okay, so guys, in a nutshell, that is essentially all you need to know for this topic. It's very short, but you just need to know some of the components. Well, you need to know the components here and what they do, and basically how a system works, of having an input, processing that information, and then based on the decision it makes, commands and output. Because microchips have multiple pins, you can actually, and the more pins you have, the more functions you can control, you can tell it to control. So yeah, if you got like like a 16 pin microchip, you've got essentially 16 pins that you can program it to do certain things. So you could have loads of different outputs connected up, and then they can all do different things based on different stimuli that it receives. Okay, so you can have a go at the practice questions now. And we've got the practice questions actually embedded in the slides here. There's also a quiz that you can look at here. I'm going to talk through what the answers would be in the screencast at the end for the practice questions.